So before we start, one of the TAs was kind enough to bring in this notebook that someone left in one of their labs. It's got very beautifully written notes in it. So if this is yours, please come claim it. And if it's not yours, I would claim it anyway, because it really is beautifully written notes. So this will be right here, if in case its owner walks in. There is a method called equals. Every class has one. Every class has one whether you define one explicitly or not. If you don't define one explicitly, then the default is if you write something like r1 dot equals r2, then that's the same as just testing whether those two references point to the same object. So reference equality is the default for equals. But a lot of classes take the opportunity to redefine equals to mean something else. So many classes define equals to compare the content of two objects, and we'll say that two objects are equals even if they're different objects, as long as they contain the same thing. So an example of a class that does that is string. The string class, let's suppose we have objects that look like this. There's a variable called s1 that references this string, and there's a variable called s2 that references this string. And another one called S3. So in this case, if we ask whether S1 is double equal to S2, well, that's false because S1 and S2 point to different objects. But if we ask whether S1 dot equals S2, then that one comes out true. Because both strings contain exactly the same characters in exactly the same order and exactly the same number. Also, if you test S2 against S3, they're equal in every way because they both point to the same object. So S2 double equal S3 is true, and S2 dot equals S3, not surprisingly, is true as well. So the first one's false, the last three are true. In homework 3, you use the equals method to compare integer objects. And integer is a class in the java.lang library. So two integers are dot equals if they contain the same integer inside them, even if they're two different objects. Any questions on this so far? Now, a lot of classes redefine equals, and they can redefine equals in a lot of different ways, depending on what it is they want to do, what it is they care about. And so there are at least 4 different degrees of equality that different classes might use in the dot equals method. And any particular class gets to pick which one it's going to use for its equals method, and usually chooses what's appropriate for the application at hand. So the simplest version is reference equality, where the equals method does exactly the same thing as equal equal. So that's the default, same object. Another one might be called shallow structural equality. So shallow structural equality means the two objects could be different objects, but what you really check is whether their contents have reference equality. So if the two objects have fields that are exactly the same, then that's shallow structural equality. But you could also talk about deep structural equality. Deep structural equality is a recursive kind of notion. Basically, two objects have deep structural equality if their fields are equals according to the equals method. And what that means, well, that depends on what kinds of references are stored in those objects. But in the case of a list, checking whether two lists have deep structural equality will typically mean going through the whole list, and even though they have different list nodes, checking whether they have the same items, or checking whether their items are equals. And I'll give an example of code that checks that shortly. And a fourth kind of equality that makes sense for a lot of special data types is logical equality, where two things sort of make sense that they're equal from a mathematical point of view. What do I mean by that? Well, let me give you a couple of examples. Suppose you have a fraction class, and one of your fractions is 1 over 3, and one of your fractions is 2 over 6. Should those two objects be equals? Well, from a mathematical point of view, yeah, they probably should be. Even though the numbers that are stored in the fields are completely different. A second example is suppose that you have set objects, which is designed to represent a mathematical set. Then two set objects should be equals if they contain the same elements. And it shouldn't matter what order those elements are stored in, because in a set, order is irrelevant. So there's a bunch of different kinds of equality you can define for your classes, and you get to pick whatever makes sense for your application. Yes, question? Mm-hmm. Mm-hmm. So if they are pointing to different nodes, then they are not structurally equal. Deeply they might be. So, I mean, as a simple example, instead of using a next and equal, let's just compare two S lists. For two S lists to have shallow structural equality, their heads have to be pointing at the same S-list node. So that's the only way you can get shallow structural equality with lists. But you can get deep structural equality with lists by having separate S-list nodes that just happen to have objects in them that are dot equals. So this is deep structural equality, but not shallow in this example. Does that make sense? Okay, great. Other questions? Mm-hmm. Uh-huh. So you're talking about whether two different classes of object are equals. Well, so that doesn't come up very often, but if you want to do that, then you can define the glist.equals class so that it's smart enough to test that. But then your dot equals method has to look and see what kind of list it's comparing against and have different code for different kinds of objects. There's nothing what? Not really. I mean, inheritance can help make it easier to code inter-object comparisons, when we'll talk about inheritance in the next 2 lectures, but that's not something I see a lot of. So let's look at some code to test this deep structural equality on S-lists. So equals has to have this signature. If you wanted to find an equals class and you want it to get called properly, then generally you do it something like this. So the first thing we're going to do is, since S-lists have a size field, we might as well compare them first. Because 2 S-lists with different sizes cannot contain the same S-list, the same list. But if their sizes are the same, let's go ahead and actually compare them node by node. I'm going to do this iteratively. You could do it recursively, but as I spoke about last class, if you do it recursively, then your code will crash on million item lists. So we'll do it iteratively. I'm going to start at the heads of both lists and walk through both lists simultaneously and just compare their items as I go through. So to do that, I'm going to have a little while loop that loops as long as the first list still has an item to compare. And then I'm just going to check whether both nodes point to the same item or different items. And if they point, question? Oh, yeah, thank you. Mistake here. There we go. Now, if we ever encounter 2 items that are not equals to each other, then we return false and stop right there. No need to check any further. But otherwise, we need to go on to the next items in each list and compare those. So we advance N1 one node forward in the list, and we do the same with N2. So now we're looking at the next node in list 1, the next node in list 2. We're going to compare them on the next iteration of the loop. And if we get all the way to the end of list 1 and everything checks out, since the size fields are the same, we assume that there's no more nodes in list 2 either, so we can go ahead and return true. Everything checked out. Now, I only guarantee this implementation will work if the S-list invariants are holding. If the size fields are lying about the size and the N2 list is really longer than the N1 list, this code won't catch that. Any questions about this? Yeah. This refers to the item that the S-list node is pointing to. Yeah, it's integer dot equals. So what that line of code is doing is it's actually comparing this with this and checking if those two are equals. So not the nodes, but the actual items. Other questions? Yeah. Yes, every class has its own equals method, and they tend to all be different. So the equals that gets called on an integer is different from the equals that gets called on an S-list. Yeah, they're two separate methods. And usually there's a different method for every class. I want to talk about code testing now. You guys are hopefully midway through implementing your first big project in this class, and then the second project will be a lot bigger. So when you're putting together a big piece of software, you're making it out of little pieces of software, namely methods. And when you put it all together into a big hunk of code and it doesn't work, it's really hard just off the bat to figure out where it's going wrong, because you're going to have bugs. The question is, where are those bugs? So I want to talk about ways to try to test individual subroutines and modules, and hopefully maybe this will help you a little bit when you're stuck, when your code's not working, trying to devise a way to get unstuck and figure out where the bug in your code is. Now, I really like CS61B, and I think that most of the material in this course is really interesting. But I have to confess that the rest of this lecture is going to be a dreadful bore, and so let's all slog through it together, and hopefully we can bond, you and I, through shared pain. There are three kinds of testing I'm going to talk about today. The first one is called modular testing, which is testing each function and each class separately, which you've already seen a lot of. The second one is called integration testing, which is where you've got a bunch of modules and classes that hopefully work individually, and now you're testing them all together. And the third kind is something called result verification, where you are testing the results of your code that come out to see if they're really correct and really or you're testing your data structures to see if they really satisfy the invariants that they're supposed to satisfy. So the first one is called modular testing, and the first half of this is kind of the obvious half, stuff that you've already been doing. We have methods. We write test code for each method. We see if the method actually returns what we're expecting. But there are actually two different kinds of modular testing, or code for modular testing. There's what's called test drivers, and there's what's called stubs, which are a less obvious idea, but one you should have in your toolbox because it'll help you out sometimes. Test drivers, their job is just to call your code, check the result that comes back, see if it makes sense. So you've seen lots of this so far in, for instance, homework 3, lab 3. Hopefully you've written a few test drivers yourself for some of the homeworks you've done, at least homework 2. Now, the question I want to address right now is where to put test drivers. And as you've seen, they're usually put into the main method. Because for a lot of classes that are meant to be called from other classes, like slist, the main method's not being used anyway, so it's just a convenient place to put test code for that particular data structure. However, sometimes you need to test an application itself that has a main method because it's the main entry point for the program. The long erasers are useless. So if you have a class that is the entry point for the program, then its main is already in use. Its main is running the program. So you need to get in from the side. And so you typically write a separate class whose sole job is to call the main class. So you have your program. And in your program, the main method's taken. But what you do is you write a little test driver class that actually does all of your tests. Okay, so all of your test code goes in here in a method called test driver or something like that. And then you write a whole other class whose sole job is to call test driver. And public static void main blah, blah, blah. And then just myprogram.testDriver. Yeah, question? Yeah. Yeah, that's 6 hard lines of work. The reason why, well, the main reason why is you can't really call the methods directly from down here because a lot of the methods you want to test might be private. And if a method is private and you need to test it, you can only really test it from inside my program. And that's why the test code needs to go here and not here, is so that you can test private methods. So if that's the situation you're in, this is the easiest way I know to do it. So now that you've done this, you can run this test code here by typing Java test my program. The less obvious idea, besides test drivers, though, is called stubs. And stubs differ from test drivers in a funny sort of way. They don't do the calling, they get called. Stubs are usually very short. Now, why would you write test code whose purpose is to get called? There's 3 different reasons why this might happen. One is your method needs to call another method. That other method hasn't been implemented yet, and it's going to be a lot of work. So what you do is to test the calling method, you replace the not yet existing called method with something that just returns dummy data that you can use to test. So it just fills in for a missing method that you have not yet implemented. A second reason why this might come up is what you think your guys are going to find is that in a lot of cases, you have a bug, but you can't tell where the bug is. Now, for instance, just because Java is throwing an exception in one method over here doesn't mean that the bug is over here. The bug might be in some other method way over there that returns a null pointer when it's never supposed to return a null pointer. And then that null pointer makes its way to some other method, and eventually that other method tries to call a method on the null pointer, and you get a null pointer exception. Oops. So you get a bug over here, but it was really caused by something far, far away. And how can you figure that out? Well, one way you determine whether the bug lies in the calling method or the caller by replacing the callee, by replacing the callee with a stub that's very simple and never returns a null pointer, but just returns something stupid that's not a null pointer, for instance. And so the stub's job is to be so simple that, and to just return simple data so that you know that whatever information you're getting back is not going to be completely wrong, and then you find out whether the caller still has problems or not. The third reason is a little more intricate and interesting and comes up all the time, though. Suppose, for instance, that you are assigned to write air traffic control software, and you want to find out what your air traffic control software does when two planes are heading directly for each other. So there's two ways you could do this test. One is you could arrange to have two planes fly directly towards each other, spend a few $1 million. The other is that you could just fake the data and feed it in to your program. So typically, an air traffic control application will call some procedure that returns the actual radar data or sonar data or whatever's being used to track these airplanes. Think about sonar data tracking airplanes. Anyway. So the point here is that you can produce test data that real subroutines rarely or never produce. And the other thing is that it's repeatable test data. So, maybe you have to try flying two planes at each other 20 or 30 times before you track down the bug. So you want to be able to reproduce that situation over and over and over again. Because if you have a certain kind of data that comes in once, and then your program crashes, and you can't make your program crash again because you can never get the same data back again, then it's very hard to find the bug. Any questions about this? The second kind of testing is called integration testing. And integration testing is just a fancy word for when you have already tested all of your modules individually to the best of your ability, and then you put them all together into some really big application, like air traffic control software, and then you test the whole thing at once. The big issue here is that integration testing is a lot harder than testing individual modules, because now when something goes wrong, it's very hard to figure out which module it went wrong in. And a lot of the time, it's not that there's any one module that's not functioning right. A lot of the time, there is a misunderstanding between different modules about how they should communicate or what kind of data they're expected to return. And this especially happens a lot on software projects where there are multiple people working together in a team. One person writes a module that manipulates lists, and they think it's supposed to work one way. The person who's calling that module thinks it's supposed to work a completely different way. And if they don't find out that they have an essential miscommunication, then they'll never understand why their software doesn't work together. So the most important task in avoiding these kinds of bugs is to define your interfaces as well and ambiguously as possible. So there should be absolutely no ambiguity in the descriptions of the behaviors of your methods. Now, when you guys get to Project 2, I bet you that you're almost certain to have some sort of problem that arises out of this. So make sure that you're meeting with your teammates often and that you really do a good job at the start of hashing out the interfaces between your components and the components that your project partner is doing. But nevertheless, despite doing your best to try to make sure your interfaces are really clear and your modules are going to work together the way they're expected to, you're still going to have bugs. And you won't always be able to figure out easily where those bugs are. So when you're actually looking to find those bugs, I can only really give you one good piece of advice, which is seriously learn to use the Java debugger. So we will introduce the debugger in an upcoming lab. And what I found historically is a lot of students do that one lab and then forget about the debugger for the rest of the semester. And I think most of them wind up spending a lot more time on their projects than they needed to as a result of that. There is a certain upfront cost learning curve in learning to use a debugger. It seems hard at first, but once you get it, you can save yourself a lot of time in the long run by using debugger to debug your code. So also the instructions for the debugger, again, are in your course reader. If you bought the red course reader from Copy Central, that's in there. So, I can't emphasize too much. Overcome the laziness barrier to do this early, and it will save you time over the course of the whole semester. The third kind of testing is result verification, which is a little bit different from the others. It sort of requires you to have a special situation where you have an algorithm that creates a very specific known result, or you have an abstract data type that has specific known variants. But if you have those things, then you can test them. So here are the two things you can do. One is you can do what's called data structure integrity checking. Basically, what this does is, well, when you define an abstract data type, if you're careful, you define some invariants for that abstract data type so that you know if your code is working right. Well, once you've got those invariants, one of the big advantages is now you can write code that tests them and reports back at the earliest time when some bug in your code breaks the invariant. So your integrity checker inspects the data structure and verifies that all the invariants are satisfied. And so in project 1, I have asked you to write a data structure integrity checker. It is called check, and what it does is it verifies that a couple of simple invariants hold for your run length encodings. And if you run that check method after every time you change your run length encoding, you can use that to find bugs early as soon as figure out where they're happening. The other kind of result verifier is what I'll call an algorithm result checker. And what this does is, after you run some algorithm that performs some task, then you check whether the result that it computed actually seems to be correct. And to give you, it's easier to make sense of that when I give a concrete example. Suppose you have a sorting algorithm. Later this semester, we're going to spend 5 lectures on sorting algorithms. So you sort a bunch of numbers in order. After you've done that, you can check whether your sorting algorithm worked by walking through the array of numbers and making sure that each number in the sequence is less than or equal to the number after it. So check that each number is less than or equal to its successor in the list. And usually it's much easier to check whether the result of an algorithm is correct than to compute the result in the first place. Now, Java has kind of a built-in feature to simplify a little bit using these checkers once you've written them. There's something called an assertion. An assertion is code that tests an invariant or a result. So here's how it works. You write something in Java like assert x is equal to 3. At some point in your code, when you think that x should always be equal to 3 at that point. So if you think it's an invariant of your data structure that x is always equal to 3 at a certain point, then you can test that. And the idea is that if x is equal to 3, this line of code does nothing. If x is not equal to 3, then this line of code throws an exception and prints out an error message so that you know that your assertion failed, and the program stops running right there. So by putting lots of assertions in your code, that means you can catch early when something has gone wrong with a data structure. Typically, a way you might use this is a little more complicated than x equals 3. You might say something like, for instance, suppose you're checking that a list's size field is correct. That's one of the invariants of the list data structure. Then you can write a little method that actually walks through the list and counts the nodes. Let's call it count length. And compare whether those two numbers come out the same. If they are, nothing happens. The insertion, the invariant holds. If they're not equal, then you want to do something. Also, the Java assert syntax allows you to throw in an error message that you print out when the assertion fails. And the way you do that is to put a little colon at the end and then put the string that you want to get printed out. So again, this string is printed out and the code stops only if the assertion fails. Now, the thing that makes assertions handy is that you can turn them on or off when you need them. So, for instance, This code here that walks through the list and counts all the nodes, that's expensive. If you've got a billion node list, that's going to take a while to run. So you don't want it to run in your production code that you send to your clients who are using your software. You only want it to run when you're testing your software. So it's easy to turn off assertions in Java, which has the effect that all of the assert code is not executed. And so here's how you do it. When you want to turn them off, when you want to turn them on, so you want to actually test your code and check all the assertions, you run Java with the -EA flag, which stands for enable assertions. And when you want to turn them back off, then Java-DA for disable assertions. And so when you turn them off, your code is fast. So we don't execute any of the assertions. When you turn them on, your code is tested. Question? Well, that's a good question. So they say that the default is supposed to be DA, disabled assertions. But I tried it on the lab machines, and there it seems to be EA by default. I'm not sure why. So don't believe everything you hear. Try it yourself. Yes? Oh, this is when you actually run the program. So when you actually run the program by typing Java slist, well, you throw in the -EA switch before the name of the program you're running, and before the command line arguments. Yes?
If you don't provide a custom error message, what does it give out? Does it say assertion failed, but that conditional?
Yeah, what it says is it prints out that there's an assertion error thrown. It prints out a stack trace. So pretty much the same thing as other exceptions, except that the exception name is assertion error. Oh, the question was, I should repeat more questions. The question was, what was the question? What is the error message that Java prints when one of your assertions fails? And the error message looks a lot like the error messages that it prints when something goes wrong and your code crashes, except that instead of printing out null pointer exception and a stack trace, it prints out assertion error and a stack trace. And then, of course, if you want some actual useful information, then you should throw in some of your own right here. Now, one thing I want to point out is that this line of code here, like this method call, is not called if you use -DA. So, in this particular case, that's good because it means your code is faster when you use -DA. But it's very important that you never put a method call inside an assertion that your code actually needs to be correct. Because then when you turn off insertions, this method is not going to get called. If your program is depending on this method being called, that's not the place to put it. Question over there. Say that again, the last part. Oh, well, yes. The try and catch can be very useful for debugging. But so I'm going to cover exceptions in a lecture, I think, next week. So we've got that coming up soon. But So you guys should at least come out of this class having heard the words regression testing. A regression test if you work for a software company as a programmer, you're going to have to deal with this. A regression test is a test suite that's coded up and that can be rerun whenever changes are made to the code. So the idea here is when you're a new programmer, it's very tempting to just write a little program that takes in your commands from the input line, like type in some numbers and I'll test using those numbers. So you type in your numbers to the command line or to the program, and it goes and does the test that you told it to do. And that way you can think up tests on the fly in your head and just type them in and watch them go. The problem with that approach is that after you've done your test, you forget about it forever. And next time the code gets changed, you might actually introduce a new bug that wasn't there before that test would have caught. So as a general idea, it's best to actually code up your tests into code that you can call over and over again and that will repeat the same tests over and over again. And in any big software company, they have huge reams of regression test code that test every possible functionality of the product so that every time a programmer makes a change somewhere in the code, the regression test that night will catch any bug that it gets introduced by that change. And the reason that's important is because that way you find the bug fast, immediately that night, instead of a month later. And the programmer who introduced the bug, you know who it is, and they still remember the change that they made, and so they have a pretty good chance of knowing why they introduced the bug. Whereas if you wait a month before you catch the bug, then they won't remember the code they wrote anymore, and no one will know where the bug is, because thousands of lines of code have been changed in the last month. So pretty much any software company, you'll be surprised to find that for most large products, there are actually more lines of test code written than lines of code in the product itself. And that's normal. That's standard in the industry. So, see you next time.